Welcome to today's webinar on additive manufacturing of metals at microscale. This product is manufactured by Exaddon based in Switzerland and is distributed here in North America by Quantum Design. So before we move on to today's webinar, let me take a few minutes to introduce you to Quantum Design for those of you who have not had a chance to interact with us in the past. Quantum Design is a manufacturer and a distributor of scientific products. In the current slide, you can see two of our most well-known systems manufactured in San Diego by Quantum Design. On the left is a squid magnetometer MPMS-3, which is now in its third generation for the initial one that was launched in 1984. The squid magnetometer is one of the most sensitive magnetometers that exists in the research community. On the right is PPMS, Physical Property Measurement System, and is used to characterize electrical, thermal, and magnetic properties of different materials. Both of these tools have been extremely popular in the condensed matter physics and material science community. And we have few thousands of these installed in worldwide universities and research institutes. Recently, Quantum Design expanded its reach in the nanoscience community when it acquired a technology from GE Tech in Vienna. This new product, ASSEM, is a miniature AFM that one could mount inside a wide variety of SEM, FIB, or helium-ion microscope. Basically, one could then perform atomic force microscopy in conjunction with a scanning electron microscope, where one uses the SEM to locate an area of interest and then perform AFM measurements on that same location. This enables material scientists to perform three-dimensional topography, perform electrical and thermal and magnetic measurements all inside the SEM. This correlative microscopy technique gives an added dimension to the microscopist who is using an SEM. So Quantum Design offers instrumentation to a wide variety of research areas as shown here in this slide. This is through a combination of products manufactured by Quantum Design and products that are manufactured by other leading instrument manufacturers, which are then distributed by us here in North America. This then brings us to the topic of today's webinar. Exaddon provides high precision and innovative additive manufacturing solutions for technology visionaries and companies aiming to be at the forefront of innovation. Their unique CERES technology is a standalone microscale 3D printing system that prints complex and pure metal objects at the microscale with submicrometer resolution. Speaking today is Exaddon CEO Edgar Hepp. With a background in business development in the technical sector, Edgar has been involved with the company from the outset, when it was still a business unit of life science and nanotech firm CERES. So we both, Edgar and myself, Ashish, we are present in the background as this is a recorded webinar. Please feel free to post your questions in the question window, and we will take all these questions and respond to them after the end of the webinar. If by chance you may have to skip and move away from the webinar, we will make sure that you get a copy of the recording of today's talk. So over to Edgar.
Hello everybody, thank you very much Ashish for the introduction. Welcome to the Additive Micromanufacturing of Metals webinar. and thank you very much for taking the time to learn more about additive micromanufacturing. Before we go into details, I'd like to give you the overview of the webinar. So what can you expect? First of all, I'd like to speak about the company Exaddon, then about the printing system, means the technology and the process, the market and use cases from our customers. Then we prepared a nice video where you can see the system, how it works, and also how to operate it, to give you a better feeling, so what the CERES system is in real, and a proof of technology maturity. And also I'd like to give you some outlook what we're doing right now and what's our ongoing development. We are solving the technological challenges of our partners by creating new additive micromanufacturing solutions. And we are also focused very much on the science environment. But next to the science, we are also working on industrial projects. So we are aiming in the long term to become an industrial solution provider. Micro dispensing itself was developed over the last decade at the ETH in Zurich, so the Technical University of Zurich in Switzerland. And in 2016, the first publication was released with 3D micrometal printing with using the system which I'm explaining you today. We took over this information and this learning from the university and developed it further to the system what we have today. 2017 we did win already awards for our technology. In 2018 we founded the company Exaddon. So we basically divested from Cytosearch, which took over originally the whole technology from the ETH, the micro dispensing technology. 2019 we already had a full supply chain in place, which is quite useful because 2020 we had 5 customers until now and systems in the field. And of course, supply chain was very mandatory to be able to handle this. We have 8 employees right now, plus external employees in the team, and we have 9 distributors in 3 continents. Very science-oriented means also we release this publication, so we write papers, we encourage our customers to write papers, we support our customers to write papers, we also do collaboration with universities if the topics are interesting for us. And as you can see, we have quite high-level paper publications written with our technology, and there is quite more possible to write because the field where we can use the technology is quite huge. Just from the beginning that you know what we're talking about, this is a CERES system, how it looks like. It's a desktop-sized system. It is located, the printer, on an anti-vibration table. There is an X and Y stage and a Z stage, very precise stages. And there is a top view camera and bottom view camera integrated to enable to make an image of the specimen where we should print on. We have the microfluidic control system and control unit underneath, which controls the printer, and we have a system computer and a proprietary developed software, which I will also explain on later pages. But before we go into the use cases, I would like to give you a short introduction of the technology. So this is really the heart of our printer, the core technology, the micro dispensing heart. You can see in the center picture, I will highlight it a little bit with a marker. There's a cantilever and there is this micro channel inside with this cantilever. This cantilever is then mounted on a plastic holder. This is a white square in the middle and it ends up in a reservoir. The reservoir here is the place where you put in the liquid you want to dispense. The reservoir is then mounted to a tubing system from the left side coming. And now, when you can imagine on the left side, on the tubing system, you apply a pressure, air pressure. The air pressure will then push the liquid through the channels all the way through the cantilever to the aperture of the pyramid on the bottom part. So this is a micro dispensing core part of our technology. And you see now in the pictures, in the middle there's a pyramid. This is how the aperture looks like. There's an opening of 300 nanometers, a tiny, tiny small opening, which allows deposition of liquids in femtoliters per second. And femtoliters per second is like 1,000,000 times smaller what the best flow sensor can detect. So it's really small. On top slide, you see how the cantilever look like more from the top angle, and in the lower picture is a schematic of the pyramid. This one is how it looks in real, so it's a consumable, we call it iron tip. Everything on the printer is built around this iron tip basically. Let's move on a little bit to the printing process. So here we see the electrochemical cell, so how we print, so what is the process behind. Again, there's a cantilever, I highlighted here, this is a cantilever, there's liquid coming out, it's getting pumped out or pushed out of the cantilever to the aperture, and we are pushing for this 3D printing an ion containing liquid, so a metal ion containing liquid out of this cantilever. Everything is in a liquid bath, so it's an electrolytic bath, so you can imagine there is a water level, which is a conductive bath basically. And we have also a counter electrode, a working electrode, and a reference electrode inside, which provides the current for reducing the ions which are coming out of our liquid to solid atoms. So basically we are pushing the metal ions out of this opening, and due to the potential we apply between counter electrode and working electrode, we get the energy to reduce these ions to solid atoms. And this happens now in the middle. You see this little dot in the middle. This is called a voxel, and a voxel is a volumetric pixel, like a 3D pixel, so to say. And we are building objects with this so-called voxels. And to summarize it, we do basically electro deposition, very local and very specific in very specific areas and controlled. From the printing process, again, you see here the voxels, so voxel number 1 and 2, you can print next to each other, you can make gaps, you can make jumps, you can print above each other, you can also do like from 4 to 5, you can make overhangs of 90 degrees with aspect ratio of 100 to 1, so you can go really far to the side without needing any kind of support structures. So pretty much this is the process we have, voxel by voxel and layer by layer. So we are starting on level Z0, and then we build always in plus Z direction our structures upwards. And this allows us now to print objects as small as 200 nanometer pillars up to 1 millimeter objects, so 1000 micrometers. The nanopillars, we ended now at 200 nanometer. We are not following this path right now, but it might be even smaller, but 200 nanometer is what we achieved so far. And we can also print up to 6 voxels per second. And the voxel itself can vary in size, in diameter, and in height. So the volume we print over time can also vary. And now we can also we can also change the pressure on the fly, which allows us to print small voxels and also big voxels in one object if required. As you're all interested in micro manufacturing, you probably know our competitors, or at least the companies also working in the micro manufacturing field or providing systems or services. I made an overview for better understanding to see where we are and also to see where the competitors are. And I clustered them in 3 parts: in metal, in polymer, and in ceramic glasses. And ceramic glasses, they use basically abrasive methods for producing their parts, so it's a little bit different than the others. Polymers, they use true photon polymerization, most likely, which is quite common right now. Nanoscribe, you probably know as company, they are well known. They are now since I think 12 years on the market, and they have been the first to really brought a system to the market. Now they have quite good competition from UpNano, for example, from Vienna. They have a very interesting system and different approach, and multiphoton optics as well from Germany, also competing in this 2-photon polymerization market. When we go to the metal, you see there is only one company which is able to produce parts from below 1 micrometer to a millimeter in size. This is us. The others, they are starting basically above a millimeter and even larger, and they use then powder bed fusions, for example. So you can have metals in larger parts with different technologies, but smaller than 1 millimeter, we are the only one on the market. About market and use cases. So we have customers working in different fields, as our technology is quite broad and versatile. So we have customers working in the neuroprosthetics and also in the HF technology, terahertz frequency, a lot of research in this field actually. We work with semiconductor customers, it's more industry-related customers. We have, of course, a Swiss company and precise technology. We are working with the watch industry. And we have also customers working in the microelectronics and potentially your application. On the next slides, I'd like to show you the cases, a few cases from our customers. About neuroprosthetics, so one example, it's a chip-brain interface. So it's this understanding of neuronal communication and also in the long term to overcome diseases. And this is a project with Purdue University. You see on the upper picture the schematic view of a neural interface device. So it's basically a device which allows to place needles or to print needles on a pattern which then get injected into the brain of a living animal. In this kind, it's like an in vivo application. So they measure the neuronal activities of the rat by stimulating the rat in different ways. And they're measuring this kind of signals, what happens there. And the device on the top part is, they need nanowires, tiny wires, very precise and with a high aspect ratio. And we are the only company and only method which allows to print wires with a diameter below a micrometer and up to 20 to 50 micrometers long and height. And this is how we use micro additive manufacturing with metal parts for neuroprosthetics applications. Here we see a typical other topic, high frequency device. It's a general device. They have many small parts there. You see the wire bonds. There are passive elements like RF waveguides. You can also think about tiny coils, which will be needed on such a chip and can be now 3D additive manufactured. This is an ALMA Band 5 receiver, which is developed from the Chalmers University of Technology. So, and also on the top view, you see, I highlighted a little bit here, this part. You see the total size. It's like a millimeter. It's a whole chip, 1.5 millimeter, and the device parts are tiny and small. And this is exactly where we kick in with our technology. Another topic, again, in the high frequency field is the problem of signal noises. Here on the left-hand side, you see again, here this is a typical wire bond connection. It's a bond wedge connection, and you see here I highlighted this one, the part is really sharp corners and edges, and this one creates a lot of noise for high frequency signals. And when you see on the right hand side, this is an example of our additive manufactured wire bond, which is of course slower in time from production. We cannot compare to standard wire bonding, but the quality what we create here on the surface, the way how we move out of the specimen, of the pad where you want to have this wire, is really, really smooth and nice. So this is one field where we can use our printing technology. Another one, also a similar way of wire bonding. It's not so much a surface, but it's to having like really interconnects which are shaped and designed, because interconnects like the wire bonds, they make noises and they disturb signals. And the shape of the wire bond can only be very limited, adjusted and defined with the wire bond system. So it goes somewhere, you just know it starts from one point and it goes to another point. But the exact shape is not very clear. So here we are having the possibility to make very nice shaped wire connections. And on the lower picture on the right side, you see we can make bridges on top of something, which allows to have a very clear defined signal transformation, and allows also to have a very defined structure of this connecting bonds. Another big advantage is the classical wire bonds. The smallest what you can get right now is about 14 micrometer wire diameter. We can go down to 2-3 micrometer wire diameter, so we can be much smaller. And due to the high resolution cameras we integrate into our system, we are able to start at tiny little pads. The contact pads can be much smaller than with traditional wire bonds, right? They have already now quite some difficulties to hit the right pad when the pad size gets too small, or they cannot reduce the pad size because they have to hit it with a wire bond. But with our technology, we can reduce the pad size down to maybe 5 by 5 micrometer, and being able to hit this and to connect from there to the next position. So this one is a HF device. Then passive HF devices. Also a possibility. We can print right on the specimen, on the microchip, with a specific shape. Coils, microantennas. We can even make other details. We can partly put gold layers on specific areas. So this is more general, but yeah, there can be your HF device or your MEMS device can be changed in a way and with objects which are not possible to produce with any other technology. Then now more industrial objects, which I also like to show you. This is one project we are working on. On the left-hand side, you see a probe card from semiconductor. It's being used for testing the devices on a wafer. You see here the pitch is 80 micrometer. So this is really the smallest you can get. So the pitch between the single lines here, the single testings is 80 micrometer. With our technology, we can go down to, as I said, the pads can be down to 5 by 5 micrometer. And so the pitch will be 10 micrometer, maybe 15 micrometer. So we are really smaller, much smaller than traditional manufactured probe card devices. Additional, this manufacturing process is quite complicated. The assembly process is quite complicated. And our goal is to print elastic testing pins directly on the carrier, which enables us to reduce the manufacturing process of such probe card by multiple steps and reduce the cost for our customers and increase the flexibility as well. One very interesting project which we are working on since quite a while, I have to say, is to print conductive lines, but directly on a computer die. So it's repair open defects on a die is one big topic for us. It is in a project in the concept phase. We already had like a master thesis working on it, and we are keep on going with it. We have semiconductor partners working with us in this field as well. And also, it's the next topic for not only repairing open defects, also connecting specific areas to level a chip. So after manufacturing, this means when a chip is manufactured and tested with the probe cards, we probably have also our part on. Then it will be tested, and potentially it's not that leveled, and you need to balance it a little bit better and or level the whole chip better, and you would like to add certain parts to the circuit of the chip, and there we can make the connections to these circuits. So this is a nice project as well. Then one more, the watchmaker industry. It's copyright protection and optical applications. So we have a customer which is very happy to have a unique object printed with our technology to underline his uniqueness. And this is also one possibility to use it for, just like for making nice objects in 3D shapes, like which you could also do with a big printer, but not in our scale, of course. Microelectronics and industry. So we have developed this part with a French customer from us, Axon Cable. They came with the need to having smaller plugs, micro plugs, On the left-hand side, you see the 1.8 millimeter plugs with gold wires. It's twisted gold wires. It's the SEM image. And you see next to it a little gold arrow, a little gold bar. This is the size you would like to have. It's like only 400 micrometer in height. They delivered the CAD model to us, which you see in the middle picture. And what we did, we printed. So you see it on then next to the CAD image, the 3D printed objects is exactly what we achieved by printing this CAD model they requested. And on the right hand side, you see the plug as a demonstrator, which is a future product from Axon Cable. And the plugs, which will we print there, are the only possibility to produce them is with our additive manufacturing technology. Fundamental research and material science is also definitely a very interesting topic for us, and especially for our customers. Here you can see the lattice, which is here scripted on the left hand side, and next to it you see the printed lattice, so it looks pretty much exactly the same. Very interesting here, as I mentioned before, horizontal printing. It's necessary for making these objects possible. Here we did a lot of horizontal printing. You can see all the beams and they're connected with vertical beams and with banded beams, and all this made this lattice possible in a very, very small scale and in metal. So we are the only one with our micro additive manufacturing technology which enables our customers to print metal lattices for their material research. We also made a test, like a spring constant test, with a tool of the company Alumnis, and executed by the Institute EMPA in Switzerland. And you see here the spring forces, or which we took the spring forces of copper. It's not the most interesting thing what you can see, but you can see especially here the connection of the one voxel to the surface where we start our object. So we start the object printing with one voxel all the way up to the platform, and it's very strong connected. This means also we have very good adhesion of our printed object to the existing structure. The adhesion forces there are very strong. It's a very nice information when you consider now a different application like wire bonds, that you know now the connection from the pad or from the surface to the wire is very strong. This helps, of course, for being sure the interconnects you're printing, they have a very good connection. Here, just some more pictures of objects we printed. For example, the pillars, different pillars in different diameters. One thing to explain, in the middle pillar, I try to make here some voxels, so it's printed with one consecutive line of voxels in Z direction, and the voxels have a certain height. And assuming now the fat boy here, they have also these voxels, just the diameter of the voxels is larger. And now by assuming the height of these two voxels is the same, the printing time would be the same. So this is just as information for giving a better understanding of printing times. Printing time varies definitively with the volume you want to print. So you can print higher volume in the same time, or you can print higher precision in the same time as you request. Here just some flat coils we printed, and like some coils and springs and flat coils. Then more complex structures. This one we did print with different pressures, so we could generate different voxels in diameter for this object. So all quite complex structures, and you see the scale bar on the bottom part. It's really tiny. It's around the diameter of a human hair, and to print complex structures like this with other technologies, it's just still not possible. And here a nice overview that you can also load many objects in the printer, and you just consecutive print them over time, overnight, over a longer period, and you get many prints, and you just like feeding the printer, and it follows your print request. Now we are coming to the video which I promised you. So here I will show you how the system looks like in real, not only in pictures. We are starting a little bit with a system overview and moving on. Here we go, this is the desktop, then the printer, this is the Z stage, XY stage, anti-vibration table, and the peripheral areas below, the aggregates. Then now we're starting how to prepare the printer. First of all, we need an ink, the print ink, the metal ion containing liquid. It's all chemicals can be easily handled, and we also have full instructions and guidelines for our customers. So here we are preparing the little volume for printing. Here we are assembling the printing chamber. This has to be done not every time, but maybe once every few days when you clean the chamber. The chamber is ready for two substrate sizes, 15 by 15 millimeter and 25 by 25 millimeter. Also, customer versions of the printing chamber are possible. So the space is defined and you can then build your own customized printing chamber inside if you want. Here we take an iron tip, like our consumable, out, and we already have the prepared micropipette. And now we are placing this 1 microliter within the reservoir I explained a few slides before. Then you're putting the iron tip into the printer. Here again we make a second one, we are just filling it, it's quite easy. Just go in with a micropipette, put the microliter of liquid, the dispensing liquid, and place it within the printer. It will then semi-automated load it, so that it will crypt automatically basically, and is then ready for use. Here we already installed now the printing chamber. We are refilling the electrolytes, electrolytic bath, into the printer. Now I would like to explain you a few slides about the printer software. Here you see on the left hand side, this is VCG, Voxel Cloud Generator. It's a MATLAB based software which is fully developed by ourselves, and this is used to load structures and to define, for example, voxel distances, voxel heights. Where you want to print your structure, you can load pre-existing structures like this pizza tower. You can load it already if you have the file, and then you can place it exactly on the position where you want to print it. In this case, we are printing this pizza tower right in the middle of the substrate. Here you see the red point where it will be printed and how it looks like with the top view camera. So we then basically save the file, and then the 3D coordinates are fixed. We are using now as a Kappa software, as a printer software, we are uploading the files we want to print. For example, this would be now the pizza tower, and potentially it would be a pillar or whatever you want. And you can print multiple of these pizza towers next after each other. You can just upload then as many pizza towers as you want to the system. And now we are in the printing process. You see it on the oscilloscope that we are already now printing. One more example is how we print on existing structures. So we choose this red object, this kind of bridge. We load it with the Voxel Cloud Generator. We saved it. Now we load the file into the Kappa software, which happens here. Now you see a structure of a specimen, of a test device. This is the bridge from the top view. Now we're moving it exactly to the position where we want to print it. Now we shift it here by 90 degrees because we want to bridge from the top to the bottom here as an example. So now we place exactly the object where we want to print, and we start the printing. After printing, so here we go, the printing is done, and we see the SEM image from the side. It was exactly printed like the objects they want to print on top of or as bridge between these two parts of the testing device or the specimen. CERES is important. It is the possibility to print and to additive manufacture metal structures, not possible with any other technology so far. It's a system which is hugely versatile. It can really used in many different use cases. We can print metals, different metals. We are working on different metals as well. It can be used for dispensing other materials, polymers or other liquids, not necessarily used for 3D printing, but maybe for just line printing and 2D printing. We also encourage our customers to develop their own customizations. So we are not actually we want that they grow and go further and becoming better. And we also support our customers by writing new publications. A few more different aspects why we are mature. So we are doing ongoing research collaborations with leading institutes. We have this full supply chain in place. We have seen the software. It's a very mature software already. We have a support and ticketing app for customers and requests of customers. So if you write something, you get a ticket number. We reply to this number until it's solved. We have extensively tested inks and products for optimal print results. And also our online user manual is quite huge and large. Here we see it. Let's go. This is a user manual, how it looks like. So it is made for providing all the information necessary to run the printer perfectly and smooth. Here is a quick starter manual. You can see that just to overview the topics, and then you can jump also to the specific field. For example, how to prepare the system. So you just click, it's interlinked, everything. Then there are all like information how you choose the right probe, how to configure the probe. How to use it. There are videos underlaid which you can see and understand that what has to be done, what is the maintenance. So it is quite big. Here is the iron tip. You can use the barcode. There is on each iron tip is a barcode which you can scan in, and you get a lot of technical information about the stiffness. You get a real image of this particular probe with a aperture, for example. Then we have the printing calibration. So how do I prepare the printing setups? What kind of like voltage do I set? What kind of pressure I do apply? All this is quite well explained that you are able to print well. Voxel Cloud Generator, we have seen it before in this video. There is also each part of the Voxel Cloud Generator is well explained. So we want that you are becoming a specialist of the system and using the system. And to make this possible, we put everything in this manual. If you want to script structures by yourself, in some cases it's better to script structures than just to slice it. It's also here is explained what is important, what are the parameters you should set and use. So it gives you really deep insight of the printer. Again, printing head, how you maintain it, how you're assembling it, how you install it if needed. Maintenance package. So what do you have to do? How do you have to clean it? How do you have to grease it? So like that you have a well-running system over time. It's important that you also have the ability to keep it on a very high level, this printer, and because everything is so small, it has to be high accurately. We have design rules, the printing chamber, in which parameters you should set your voxel diameters, heights, to get a better, to get good results. Here's the insights about the probes, iron tip. So what are the geometrical limitations? So it's really, we try to be as open as possible and explain and give you all the needed information you need to be able to run the printer on a very professional level. Of course, the last chapter is troubleshooting. Whenever we find something new which can occur, we write it down that you are able to run the printer smoothly by yourself. Keep on developing. We're releasing copper products and after-sales items, so everything you need to print copper in high quality is available. You can either also purchase prints from us if you want the print inks. You can also develop your own ones. We are finalizing gold products right now, so that our system is able to to print gold in a very high quality level. We're also developing nickel as print material, which will take a little bit longer, but this has magnetic, can be used for magnetic applications. It's hard material, has a high Young modulus, high yield strength, etc. This is different than copper, which is very conductive, or gold. So it's a material for different purposes. We are testing with Empire and other universities, writing papers, and we are continuously improving our technology and the softwares we are releasing to our customers for free. So yeah, we keep on going. And if you want to meet us, we are also exhibiting on different fairs. Now due to COVID, a little bit reduced, but we hope that we are next year back. We are also sponsoring fairs and conferences, being there where our customers are, being there where our partners and collaborative partners are. At the end, this is a print process, printing at room temperature, local electrochemical deposition, multiple metals, overhanging structures. This is how the system looks like. It's definitively a system for innovators and visionaries in additive micromanufacturing. So how you can interact with us, you can send us your object design by CAD file, you can detail your specific needs, object size, print, substrate, materials, applications, etc. You can request a video conference. Of course, you can contact our distributors, QD in the USA directly, and he will be the first contact for our US customers. But apart of this, we are open. You can reach us on multiple channels. And now I would like to thank you very much for taking your time for listening. And let's go to the question and answers. And I hope you have some nice questions, which I can.
Okay. Thank you for participating. I will be happy to take over some of the questions that various participants have asked. I will go on with the first question. I think Edgar is here too. Let me unmute him. Edgar, can you unmute yourself? And
yes, yeah, that's
good. Good. Yeah. So, yeah, thank you. The first question is, can you print other materials than copper?
Yeah, thanks, Ashish. Yeah, we can print other materials in copper. As I mentioned, nickel is on the way, so it will take a little while. Gold we did, and we have it as a product, as copper. And we have experience with platinum and also with silver. These are not a product yet, there are not so many requests, but it's doable, and we did some prints already, so we have some showcases there.
Okay. The other question is, do the printed voxels have voids or pores, or are they completely solid?
Yeah, it's a very good question. As we print voxels, we could assume there are voids inside or something, but in fact it's not. It's a very dense material, so we made many cross-section analyses with etching, and we have a 99.5 and even more pure copper metal. When you consider it a little bit, in a semiconductor, we are using an electroplating process, which is used in semiconductor widely, and they have high quality copper as well. So, and we are basically producing the same, but in 3D shapes.
Okay. The other question is, how do you connect these printed objects to other devices like electronics? And in continuation, does the substrate have to be made of the same material as the printed object?
Okay, the first part, so we usually print where we need the part. So we do not print and remove normally. We are not removing the parts. However, we just had a customer, a university in Japan. They would like to have metal parts and handling separately. So what we did, we print on an elastic foil, which can be moved and has a different
elastic behavior than the metal part, and you can really take off the metal parts with micromanipulator. So yeah, it is a little bit a complex process, but if you want to have specific shapes of pure metal objects without any connection to a carrier, there are possibilities to take it off. And the other question is, yeah, we can print with our inks on different materials, different carriers. Of course, copper is a great match. Copper gold is a great match. Copper ITO works very well. On PDOT, like on transparent conductive oxide, we can also print. Not all metals can be combined, because as we're using electroplating process, it could happen that we dissolve the other metal. If, for example, aluminium and copper will not work, because if you would print on aluminium, the copper will be reduced, but the aluminium will be like also reduced, so it will disappear. So you cannot combine everything. But what we did there, we made a very thin protection layer of only 200 nanometer above this surface, and then it works again. So the layer has to be very thin, and we can still print then with different materials. Like we had exactly this case, we had copper, and then we had to take a very thin protective layer on top of it, and then we could print on it.
Okay. Thank you. I hope that answers the question. If you have follow-up question, please let me know. Yeah. Can the system print oxide materials?
Oxide materials, yeah, in a certain way we could. We don't want, because there is, like, when we generate hydrogen, there is a possibility that there is oxide inside, because the water, the electrolytic bath, what we're using is water-based, and there is a possibility that oxide oxides right away by printing. But if you want to have smooth and straight surfaces, it's not something we want to be. So we have to be in a regime where we do not create like side effects and unliked process parameters, which would be an oxide step, for example. So yeah, it's tricky. We never really did it, so we just have seen it. When we go in this regime, we get problems with printing. I would not recommend it right now.
Okay, thank you. Let's move on to the next question. How many voxels can be printed with one iron tip? How long did it take, for example, to make the David that you had showed earlier?
So we can print, it depends a little bit on the structure, but right now we're printing about 500, 600,000 voxels with the iron tip, so we are getting longer and longer. And the David, for example, it's a 1 millimeter object, tall object, and it consists about 360,000 voxels. So there are quite many movements to make this object appearing like it is.
Okay. Can one print aluminium?
Aluminium is not possible to. It's basically, when it can be electroplated, it can be 3D printed with our technology, but aluminium cannot be electroplated, and therefore we cannot print it.
Okay. There's another follow-up question. Could you print tantalum oxide? I think you answered the question about the oxide part, but yeah, I think maybe this question was posted before. But, could you give an approximate cost of a typically configured system?
Yeah, this is we are starting at about $300,000 US. It comes then with it will be installed at your site. You will also receive a training. It has 12 months warranty, and you get a starter kit, which allows you to start a print right away. And it's very necessary for us that we give and provide also the nice introduction into the system. So it's really, we are coming to your place, we're gonna install it, we give the training until we really know how to use it, and this is about $300,000 US. But of course, I mean, there are always options for warranty extension, etc.
Certainly, and I think the cost of consumables and all those things would be very crucial, right?
The consumables. Yeah, it's the consumables is $175 US, and usually you can print if you take care of it 1-2 days with it, and you can also consecutive print many objects. So it's, I think, quite reasonable.
Are there possibilities to increase movement speed, and is that the time limiting factor?
Once again?
Are there possibilities to increase the movement speed, and is that the time limiting factor?
The time limiting, so the printing speed, the time limiting factor is the electrochemical reaction. So we have seen now in this presentation only 3D metal prints, but we could also dispense any kind of liquid. So we could place, or what we also did in the past, some customers are doing it, they're dispensing other chemicals on flat surfaces. And if you want to dispense an oil or a polymer or like nanoparticles out of a liquid or with a liquid carrier, the printing speed can be much higher, to 150 micrometer per second. So it can move very fast. So the stage, what we have, can move fast. For 3D metal printing, the limiting factor is the electrochemical reaction time.
Okay, thank you. Are there any more questions left? If you want me to unmute anyone, I'll be happy to unmute you. So if you want to ask the question, please raise your hand and I will unmute you for you to verbally ask a question. I think Sheely, let me ask you. Lee, do you want to ask a question?
Yes, thank you. Yeah, thank you for the great talk. So yeah, there's a lot of questions about different materials. So I would just want to go that direction a bit further. I mean, this looks like a great platform that can allow different design and innovation. So what is the technology? I mean, technically, what is the challenge for the user, say, to create their own ink per se? You know, just their own material, their own material they want to do. What are the technical challenges? Do you think they can do that, or this has to be done by the company? Thank you.
Yeah, it's a very good question, very valuable question. As I said a few times, we really encourage our customers to develop their own inks. So we provide it for the people who just want to print. Then we have a portfolio of several inks. But so what is the challenge? So the challenge is to find the right spot where the reduction of the metal is not too slow and not too fast. For example, that the system and the electroplating speed works well hand in hand. So the voxel we are printing, so each voxel we are printing, we are measuring with a laser deflection of this cantilever, and this has to match pretty much the speed of the system. I would say it's more an electrochemical challenge to develop the metal than this would be. I would say 70% is electrochemistry and 30% is getting the understanding combination of electrochemistry and our system. But all of this information we provide, so we really give you the information how we calibrate copper, for example. We do also calibrate gold, so there are calibration tasks behind, and this can be developed for other materials. But it's not something you do usually in 2 weeks work, so you really have to spend some time for it. But yeah, this is electrochemical is the main focus. And if you want to dispense other materials, there are different topics you have to consider, like the viscosity of the material. Does it stick to the surface? Is this hydrophile or hydrophobic? Though there you would need to consider other things. There will be quite some trial and testing.
Thank you. Yeah, if I may, one more question. So for with the two-photon technology, they can print also very tiny structures like this. And is there a possibility for them to coat those structures printed with metal? And how would you compare those to what you create here?
Two-photon polymerization, there are quite some papers out. They did try to get some metal parts in it and then to bake it out and to sinter it, but it's not really working. So it really works very well for polymers, but not for metal structures. Yes, everyone who has a nanoscrap system who is a little bit interested in the conductive materials, they have to coat their objects. And then you have a coated polymer objects. This is the way, like there are many papers out where people exactly did it like this. The biggest difference is that we can really print pure metal and from the core to the outside, and we can also start at a certain point, and there is a strong connection to the surface where you start with it. So it's not really comparable. I mean, I think maybe we could combine it. There are ideas to combine these two technologies. So if you have a nanoscribe, you could probably coat a certain part, and then we could print some metal. So this flexibility might be given, but they are really not comparable from the purpose, because it's basic plastic and metal what we have. And we can not 3D print plastic polymers. We can do 2D dispense it, and they cannot do metal 3D printing. So this is the biggest difference.
Great, thank you very much.
Thank you, Lee.
All right, Edgar, thank you very much for your excellent presentation and answering the questions from different scientists here. We will be